Hi, welcome to a new session of Circuits and Networks. In today's class 3, under Basics of Electrical Circuits and Networks, we are going to see the problems which are related to KVL, KCL applications, as well as some numericals which are based on dependent sources. So how to solve this kind of problems we are going to see here. So before jumping into the concept, let us see what exactly Kirchhoff's current law states. So it states that the algebraic sum of the currents entering at a particular node is zero, or in some texts you can also see this definition that at a particular node or a point or a junction, the incoming currents is equal to the outgoing currents. In order to understand this concept, let us jump into the example 1, where you can see you have two nodes, and between two nodes, three branches are placed, and three branches are carrying current 3 amperes, 8 amperes, and IA. We need to find out the unknown current IA. So here I can consider node 1 or node 2, and after that I have to see whether the current in the branch it is incoming or outgoing. For instance, if at all I take the node 1, where current IB and IC and IA are flowing from node 1 to node 2, only the difference is that IC it is flowing opposite to the convention of IB and IA. So at this node 1, uh, if at all I apply the KCL, I'm going to get IB plus IA. I'm treating the outgoing currents, that is IB and IA are outgoing from node 1 as positive, and IC as incoming current as negative, and the sum of the currents at a particular node is equal to 0. With that, the value, if at all you substitute, I'm going to get IA is equal to IC minus IB. IC is given as 8 and IB is given as 3 according to the convention framed. So with that, I'm going to get the value of IA, which is nothing but equal to 5 amperes. Now, if at all you look into the node 2, the 5 amperes and 3 amperes are incoming and 8 amperes is outgoing. So this also satisfies Kirchhoff's current law. In another example, you can see there is a loop which is having the known currents as 1 ampere, 2 ampere, and 5 amperes. We need to find out what is branch current I1, I2, and I3. For this, the node points are framed already. So let us name these nodes as A, B, C, D. Now at node A, you can see current I1 and 2 amperes. It is going away from node A, and the incoming current towards node A is 5. Therefore, at a particular node, the incoming currents is equal to the outgoing currents. With that, we'll get the value of I1 is equal to 3 amperes. The same logic will apply, that is the KCL when it is applied at node B. You're going to get I1 plus 2 is equal to I2. So I2 current would be, since we got the value of I1 as 3 amperes, I'm substituting that in this equation. I'm going to get the value of I2, which is equal to 5 amperes. Okay. Similarly, at node C, I2 is incoming, I3 and 1 ampere are outgoing. Therefore, I2 is equal to 1 plus I3. With that, I'm going to get the value of I3 is equal to 4 amperes. So you can cross check the result by your own method, that is apply a converse approach to the approach what we have done over here. Let us go into the example 3, where you need to find out the currents IA, IB, IC, and ID. Now clearly you can see ID, if at all you look into this particular branch, it is connected to this particular node over here, where 2 amperes and 5 amperes are incoming and ID is outgoing. So with that, I'm going to get the value of ID, which is equal to uh, 7 amperes. Similarly, IA, you can see we have started with IA here. So IA is equal to 4 and ID is equal to 7, as I told you. Just cross check these values. Now, once this is done, IB you can see 2 amperes is incoming. ID is also incoming, but ID we have done already as 7 amperes. Okay, so when substituting all these values in the center equation, where you have minus IA, which is incoming, minus IB, which is also incoming over this particular center node, plus IC is going away from the node, and 5, it is also going away from the node. With this, I'm going to get the value of IC is equal to 8 amperes. You can cross check the result with your own approach. Let us find another unknown parameters v0 and i0, for example 4. Now this is an interesting problem where you have a dependent source. Dependent source is nothing but current dependent current source is there. You can see the value is 0, given as 0.8 i0, whereas this i0 is flowing in 4 ohms. So what is the important catch over here? That voltage in a parallel circuit, this 5 amperes, this 4 ohms, and 0.8 i0 current dependent current source all are in parallel. So for that, voltage will always be the same, that is the v0. Okay, so here you can see at this particular node, which is in the parallel combination, 0.8 i0 it is incoming. Okay, 5 amperes is also incoming, which is equal to the current i0. Is this clear? This is the KCL applied to this particular node. Now if at all you take i0 on one side and constant phi on another side, I'm going to get I0 is equal to 25 amperes. I hope you understood this method. Just we have taken incoming currents is equal to outgoing currents. With that, we got the value of I0 is equal to 25 amperes. Now, what is the other parameter we should calculate? V0. V0 is a voltage measurement across 4 ohms. According to Ohm's law, V equal to IR. So, what is the current flowing into the 4? That is I0. I0 is 25 amperes. So, 4 into 25 it becomes 100 volts. So this is how you calculate the unknown parameters under dependent sources approach. Let us go with another example of finding V0 and I0 in this particular uh, circuit, which is arranged all the elements in parallel. So when you see these kind of circuits, when they are mostly in parallel arrangement, better you apply KCL only. Now V0 is nothing but the voltage across 8 ohms. V0 is also the voltage across 2 ohms. V0 is a voltage across 6 amperes, and it is also the voltage across 1 by 4 I0. So commonly I'm taking the node voltage as V0. The upper potential positive, the lower potential as negative. Now exactly V0 is over here, and I0, which is nothing but it's a value can be determined with the help of Ohm's law. That is V equal to IR. Therefore, I is equal to V by R. Therefore, I0 is equal to V0 by 2. So this is an important catch over here. So that is the first thing you should keep in your mind. Now frame the KCL equation, that is the sum of the currents at a particular node is equal to 0. Now assuming V0 to be at higher potential, first I'll take V0 by 2 and V0 by 8 as two branch currents, and incoming current here it is minus 6 amperes. Similarly, another incoming current, that is current dependent current source, you can see here I0 by 4. Now equating this equivalent to 0, and also remembering that I0 is nothing but V0 by 2. So these two equations I'm framing as 1 and 2, and substituting equation 2 in equation 1, I'm going to get V0 by 2 plus V0 by 8 minus 6 minus this I0 is nothing but V0 by 2. 2 into 4 is 8. So V0 by 8 is equal to 0. Positive V0 by 8, negative V0 by 8, they get cancelled by each other, and we're going to left over with V0. So V0 it will become here at as 12 volts, because 6 goes to the right hand side and 2 multiplied with 6 becomes 12 volts. Once the value of V0 is obtained from equation 2, you can get the value of I0, which is nothing but equal to 6 amperes. So it is also an interesting problem. Please make a note of this particular problem. Now when you look into the definition of Kirchhoff's voltage law, it says that the algebraic sum of the voltages in a circuit, or we call also as mesh or a loop, or simply a closed network, is 0. When you apply this in example 6, you can see here, fortunately the resistor values are not given. You can check in these two resistor parameters. Here the resistance value is not given, here the resistance value is not given. So you need not worry about the resistances when voltages are mentioned, because we are applying Kirchhoff's voltage law. The algebraic sum of the voltages in a closed circuit is 0, or closed network is 0, sorry. So when you apply this, I'm going to take a clockwise direction in this fashion, and I'll start with minus 10. Minus 10 plus 2 plus VA equal to 0. With that, I'm going to get the value of VA is equal to 8 volts. See here, we have directly 10 volts, we have 2 volts, and we have an unknown voltage measurement as VA. So that VA we can obtain as the difference of these two voltages, that is generally as 8 volts. Let us go into the next example. For better understanding, we need to find out V0 over here. You can see here there is a closed circuit, but it's a voltage dependent voltage source. It's quite interesting here. 2V0, it becomes a voltage dependent voltage source. And where exactly this V0? It is V0 is across 6 ohms, and the positive symbol is on right side, negative symbol is on this side. Now, when we apply the Kirchhoff's voltage law, assuming the current to be flowing in clockwise direction in this fashion. So from the sign conventions, I'm starting with minus 12 plus 4 into I, that is the drop across 4 ohms, plus 2V0, that is we are taking as it is the value of the voltage dependent voltage source, that is 2V0, minus 4 is the value of voltage exactly given here. So minus 4 plus 6i, 6i equal to 0. This becomes one equation. Another equation you can see V0. V0 is a measurement of voltage across 6. In that 6i is flowing. But according to the convention of the given problem, the minus sign is giving a counter direction to our assumed clockwise direction. So V0 is equal to minus 6i. These two equations we are framing as equation 3 and equation 4, and later we'll substitute equation 4 in equation 3. Then we are going to get minus 12 plus 4i. This 2 multiplied with minus 6i becomes minus 12i. Minus 4 plus 6i as it is equal to 0. With that, I'm going to get the value of I, which is equal to minus 8 amperes. Now, when you substitute this I equal to minus 8 amperes in equation 4, I'm going to get the value of V0 as 48 volts. So you can see we have listed out 7 different examples for Kirchhoff's voltage law and current law conditions, and we have solved majorly the problems which are involved with dependent sources. And we have seen also the beautiful concepts, whether the resistors are given or not, we can easily find out the value of voltage if at all the other branch voltages are given. So that's all for today's class. I hope you like this particular session. Please share among your friends, subscribe to this channel, and please press the bell icon for future notifications. Thank you.